Welcome to part 2 of Global Wind's discussion for the Earth Science class. So in part 1, we looked at atmospheric pressure and how that pressure relates to the weight of the gases. We found that living in the troposphere, the weight is dominant on the surface, which produces about a 15 pound per square inch atmospheric pressure. And as you ascend in the atmosphere and get higher and higher, pressure decreases or the weight of the atmosphere increases. We looked at low and high pressure systems, and we took the high and low pressure systems and related it to wind. And we found that wind is produced from high pressure systems that are moving into low pressure systems. And if you're in between a low pressure and high pressure system, you'll experience possibly some type of breeze or wind depending on the pressure differential. We also looked at day and nighttime coastal breezes, and we related that to how the Earth heats with respect to the specific heat properties of the Earth, meaning that the Earth's land will heat fast and cool fast, and the Earth's waters will heat slow and cool slow. And because of that unequal heating across the Earth's surface, produces different warming of the atmosphere relationships, meaning that parts of the atmosphere will be warm, parts of it will be cool, and so forth, setting up pressure differentials. And then finally, in part 1, we looked at the Coriolis effect and how that relates to the circulation and processes within the atmosphere. And we found that the Earth is rotating at about 1,000 miles per hour. And because of that, winds and processes will be deflected in the right or to the right in the northern hemisphere and deflected to the left in the southern hemisphere. So this now brings us again to part 2 of the discussion, where we'll start putting together the relationship between the Coriolis effect and high and low pressure systems. So in this first slide, we are looking in the northern hemisphere. And again, that's where winds and processes in the atmosphere are deflected to the right. And in terms of the high pressure system, now we're going to refer that to an anticyclone. So high pressure systems are also known as an anticyclone because we're now going to consider the Coriolis effect and how the Earth rotates. And so looking at a high pressure system, we already know that that is subsiding and sinking air. So in the northern hemisphere, air will typically in a high pressure system spiral downward and outward. So we go downward and outward, and this would be a clockwise out spiral. Low pressures, on the other hand, air will spiral upwards and inwards, and we would certainly expect that because low pressures being rising air, high pressures being sinking air. So if we come down to the southern hemisphere, then this is a counterclockwise out spiral, but still the high pressure is sinking, but in this case, it's counterclockwise. And then in the low pressure is a clockwise spiral. So where we live in the northern hemisphere, we experience high and low pressures in the upper part of the diagram. This next diagram kind of gives you a three-dimensional look at the anticyclone and cyclone. And so again, if we go over to the low pressure system, we see that air is rising inwards and upwards. And so this kind of gives you that 3D effect. And now we can actually consider what happens to it adiabatically. And if you remember learning from the atmosphere discussion, we learned that atmosphere or adiabatic processes involve heating and cooling of an air mass as it rises or falls. And you recall that when air mass rises, it's going to adiabatically cool because of the decrease in air pressure. And as it adiabatically cools, it's going to reach relative humidity 100% and reach LCL and produce clouds. So typically during a cyclone or low air pressure, it's typically associated with cloudy and rainy weather. So here you can see where the air is rising, and again, it gets cooler and cooler. Once it cools, it reaches dew point, and it's going to be making clouds and bad weather. And so again, low pressure systems are typically associated with bad weather or rainy weather, cloudy weather. On the other hand, if we come down to high pressure systems, again, air is subsiding, so it's moving downward and upward. And here you see the air is now moving downward. And we learn from adiabatic processes that when air moves downward, it begins to compress and become warmer. And so the air warms, it starts to move away from dew point, so there isn't any condensation taking place. And now anticyclones, high pressure systems, are related to good weather. So when you watch the news, the weather stations, and they talk about low pressures and high pressures, you'll always hear that the high pressure system is associated with good weather. Low pressure systems are associated with bad weather, all due to the relationship with adiabatic processes. So let's kind of shift gears a little bit, and let's look at how global winds are affected by the heating of the Earth. So for example, in this particular slide you're looking at, you see that the Earth is curved, and that is the popular belief that our Earth is actually an oblate sphere and not flat. And based on the curvature, the sunlight or the radiation from the sun will penetrate the Earth's surface at different angles. And depending on the angle will depending on how the atmosphere is heated. So for example, if you watch my arrow and look at the equatorial zone, you'll see that typically along the equatorial zone, the radiation is more intense, it's hotter, and therefore it starts to heat up the air a lot faster than it would, for example, in the polar areas. If you notice the polar areas, the angle of the Earth has changed, and so the radiation is not as direct from the sun, therefore it doesn't cool up as fast. And so what you create then in terms of a global wind is you start producing hot weather along the equator, or hot air. So hot air rises, which now creates a low pressure system. Then in the polar areas, you have cooler air, which is now going to be sinking, creating a high pressure system. And what did we learn then about a high pressure system juxtaposed or next to a low pressure system? Well, that's going to create wind, because the high pressure is going to want to move in to the low pressure. So on a global scale, we can look at this slide, and here is where air is sinking and becoming a high pressure system, so cold air sinks. And then here at the equatorial zone, hot air rises, a low pressure system. And you can see then by following these arrows, it now sets up a huge convection loop. And this would be considered a global convection loop. And there's the word convection. And so if the Earth was not under the influence of the Coriolis effect, if the Earth was just standing still, then what would happen is basically there would be one huge wind cell. It would be this entire wind cell, or this entire convection cell. But we know that the Earth is not sitting still, and we know that the Earth is under the influence of the Coriolis effect, which is rotating 1,000 miles per hour. And so because of that rotation and that Coriolis effect, it actually takes this huge wind cell, or this huge convection cell, this one singular cell, and splits it up into 3 global wind cells. And so we're going to just look at the northern hemisphere, and we're going to look at the effect from the Coriolis force on the convection cell. So we can look at this cell right here. This is known as the Hadley cell. And so the Hadley cell lies between the 30-degree latitude and the equatorial latitude. And you can see here we have low pressure rising, and then you have high pressure sinking, and it creates a single cell right here. And remember that high pressure is known for good weather. And so typically along the 30-degree latitude on Earth, you'll come across a lot of desert regions along the air masses, because remember, the high pressure is air that is sinking. It's warmer air, and you don't get as much rain and clouds and so forth. Then there is the Ferrel cell. That's the B cell here. That lies within the mid latitudes. It's less well defined as a convective cells. Air flows towards the north and is deflected to the right. And the Ferrel cell is the typical cell that is responsible for most of our global weather patterns across the United States. And for example, many times during the winter time, even in the summertime, storms will emanate from the Gulf of near Alaska, and it'll move towards down the west coast of North America. Then it enters California, and then the storm typically will sweep across the United States to the west. And that's usually typical storm tracks, again, due to the influence of the Ferrel cell. Then there is the polar cell, which is marked by C here. Polar cell is characteristics of cold, frigid air that is towards the 60-degree parallel latitude. And typically here, air moves away from the pole and is deflected to the right. So here in this picture, you can envision and see the entire convective cell that we showed earlier in the earlier slide. But in this case, we have now added the rotation of the Earth, where materials are deflected to the right in the northern hemisphere, which now breaks up that one big convective cell we looked at earlier into the three cells: Hadley cell, the Ferrel cell, and the polar cell. And of course, here's the intertropical convergence zone. And you can see that here air is rising both in the southern hemisphere, air is rising in the north hemisphere along the equatorial zone, which is convergence between the north and the south hemispheres. And there's really no winds that take place along the equatorial zone. This is a little animation that kind of gives you an idea of the three major global wind cells in the northern hemisphere. So again, here is the Hadley cell. Here is the Ferrel cell, which influences our weather across the United States. And here is the polar cell. And you can certainly see the high pressure zone here, and you can see a low pressure zone here in which the air is rising, and here the air is falling. This particular slide caught my interest because it shows the type of wind cells that were primarily used during the time that the Earth was being explored by explorers way before the motors became in the boats and so forth. And you always hear about explorers coming over from Europe, for example, exploring the United States. And to get there, they've always had to take what they call the northeast trade winds. If you follow my arrow, they follow along the northeast trade winds. And on the way back to Europe, they had to take the westerlies. And sometimes the ships would get caught down here into the equatorial zone on their way across the Atlantic. And depending on the season, they would get stuck in the equatorial zone, which is known as the doldrums. And recall that we said along the equator, intertropical convergence zone, we said that there are no winds. There's a convergence zone between the north and southern hemispheres. And along that convergence zone, again, there's no winds. So when the ships, sailing ships, would get caught in the doldrums, it would actually take months before the seasonal changes take place to allow them to get back in the wind systems. And so lots of lives were lost during that time because, of course, they ran out of water and food and so forth. And I thought this was interesting because I remember studying my histories back in junior high and high school days. We talked about the easterlies, the westerlies, the northeast trade winds, and so forth. But now, from an earth science point of view and from a global wind point of view, we can now attach the type of global wind cells that are associated with each one of those winds. So, for example, the Hadley cell is related to the northeast trade winds, and then the westerlies is noted for the Ferrel cell, and then the easterlies are noted for the polar cell. And so it would be quite interesting then if the explorers were moving across the Atlantic, they'd be taking the Hadley cell. Then on the way back to Europe, they would get into the winds created from the Ferrel cell. So I thought this was pretty interesting to kind of put this relationship together, with history and then a little bit of global wind science. So for the exam, you should also be familiar with the fact that the westerlies are part of the Ferrel cell, or northeast trade winds part of the Hadley, and the easterlies part of the polar cell. So you need to put that relationship together. Let's talk about the upper part of the atmosphere, and let's talk about winds that blow aloft, or winds. In this particular, we look at the jet stream. And the jet stream is a type of wind, again, that exists in the upper atmosphere. It represents very narrow zones of high wind speeds. It's a result of extremely strong atmospheric pressure gradients, meaning that there's a huge difference between a high pressure system, difference meaning a difference in pressure. So between a high pressure system and a low pressure system. Generally, these jet streams are located in the mid latitudes on the Earth, 35 to 65 degrees latitude. Again, they're found up in the stratosphere at about 30,000 to 40,000 feet. Wind speeds range from about 170 to 280 miles an hour. And if you look down here at the bottom slide, you can see where this arrow indicates a jet stream and this narrow band of wind. And so these jet streams move awful fast. And I remember there was a time many years ago that I flew to Washington, D.C. We left the Seattle area. And normally it was basically a 5-hour flight to get across the United States. And we made it basically in 3.5 hours because the pilot said that we were able to ride along the jet stream as it helped propel the airplane, to the east, into Washington, D.C. But coming back, about a week later, I came back. The pilot said we had to fight against the jet stream. And so we moved from D.C. to Seattle, but this time it took over 5 hours. So just because I gained a little time going over there, I lost that same amount of time coming back. But it was interesting to know that we can be in these high-powered winds. And then here you can see the jet stream, where the velocity of it's in the middle of the jet stream is a lot faster than the outer portions of the jet stream. Okay, folks, that concludes this section on global winds, part 1 and part 2.